1.1 is called Propositional Logic. Now, the chapter that we're going to do with first couple of weeks is on logic. And when we say logic, we mean really formal logic. And so what is this then, this propositional logic? So that's a key concept here that we're going to use, proposition. What is a proposition? A proposition is a statement that is either true or false. So either true or false. Of course not both, and not, it has to be one of them. So an example of a statement is that 2 plus 3 is 5. That is a statement. Okay, so that's a proposition. So here are examples. 2 plus 3 equals 5. Okay, the sun is shining. That's another proposition, because either true or false, right? You look outside, is the sun shining? I mean, if it's at night, then it's not. Or is it rainy, then it's not. Okay, what is not? So these are propositions. So these are propositions, not propositions. Examples of not propositions is what is the time? It's not a proposition because it's a question. Okay. Even if it's a yes or no question, it's a question, not a statement. Okay, it depends on what the person that answers says. It is not a statement. It's not that everybody can agree that this is true or false. Of course, there's another issue, right? 2 plus 3 is 5. Okay, we all agree that it's true. The sun is shining. Okay, there might be some debate if it's like overcast. Okay, so it's sometimes not so easy to verify that something is actually true or false. Especially when we talk about sentences from statements about daily life. For instance, the statement "sun is shining" is also something that depends on the moment that I'm asking, and that's a little bit of something that we have to be a little bit careful about when we use this in common language in our natural speech. But when we say this chapter is on logic, we mean formal logic, and we're talking about mathematical truths and mathematical falsities. Okay, so there is then no question that something is true or false. Now, that doesn't mean that you always know whether something is true or false. Yeah, here's an example of a sentence that we don't know. There are infinitely many primes, and we'll talk about prime numbers later, but I hope everybody knows what a prime number is. A number that's only divisible by 1 in itself. P such that P plus 2 is also prime. Okay, this is a statement because it's either true that there are infinitely many, or it's not true, there are only finitely many. There's only two options here. So it's either true or false. But the current mathematical knowledge, we don't know the answer to this. First of all, you might say, well, is this ever going to happen? Yeah, if, for instance, P is 101 and P equals P plus 2 is 103. So these are two prime numbers, you can check. There are many more, I'm just giving these the smaller ones. For instance, 41 and 43 is a pair. These are called twin pairs. Twin primes. So these are twin primes. But we don't know whether there are infinitely many or not. But it is a statement. So there's a difference between knowing that the statement is true or false, or the fact that it is a statement, that it is a proposition. Now, another thing that is not a proposition that we see a lot of in mathematics is x plus 3 equals 7 over 6. This is an equation. It's not a statement. If I say what x is, then it becomes a statement. X plus 3 is 6, that's not a statement. But it's not a proposition, sorry, I keep saying statement, I mean proposition. But for instance, if I say x plus 3 is 6 and x is 5, that is a statement because it's either true or false. And in this case, it would be false, of course. Okay? Now, we are not so much, we will use some propositions about daily life or even mathematics, and so we will use them. But what we really want to do, and what propositional logic is the logic where we work with propositions without actually knowing what the propositions are. In other words, we're going to take propositional variables. So a propositional variable, and there will be something like P, Q, R, P, Q, R, some of these letters similar in that range we usually use, but in principle we can use any letter. And what does that mean? It means it's P, if we use P in some context, then we mean that P stands for a proposition. But which proposition, it doesn't matter. So what we were trying to do is find general mathematical manipulations, the mathematics of these propositional variables. What is true, what is always true, what is never true, things like that. Okay, so that's what a proposition. Now it will become more clear once we start working with it. So I'll start working with it right away. I told you before, these lecture videos are kind of a summary and an emphasis on the main important things, but you need to read the rest of the textbook too, because there is a lot of examples and side remarks and so on that I'm not always cover in this video. So these lecture videos do not cover everything. Make sure that you read everything and that you, especially that you get more examples as well. So, but let me now start with talking about what did I mean with propositional logic, or sometimes people call it propositional calculus, namely you do calculations with propositions. So the first thing is that we're going to do operations. So we have operations on propositional variables. Like we can add numbers and multiply them, divide by them. We're going to do the same thing with propositional variables. What can we do? For instance, an example is not P. So this is read not P, and this is called the negation. So this is a negation operator. And so what is the meaning? It's what we expect it to be. If P is true, then not P will be false. If P is false, then not P will be true. So you keep in mind, and this might be something that you feel weird about, that is that when I say propositional variables, that means they are propositions. They can be false propositions. There's nothing wrong using a false proposition. That might be sound weird or sound contradictory, but you'll see we need sometimes to think about falseness as well. Okay, so it's when I say P is true, and especially here you see it, because if I apply it to a true statement, not P becomes a false statement. There's nothing you can do about that. So therefore, sometimes we want to apply this to a false statement so that we can make it into true statement. You see, that's why false and true both have to be accepted. Now, in the textbook, they use T for true and F for false, but nowadays it's much more common to use. So we're going to use this. A propositional variable can have two values. P is 0 means false, and 1. So if the variable is 0, then it's false. If it's 1, then it's true. It's easier to write. It also comes much more closer to what we would do in bit operations, binary. You'll see it all is related to that. And then the key tool that we're going to work with, not just in this particular section, but in many sections to follow, and therefore it's an important tool, understand it very well, is a truth table. So I'm going to do, I started with operations, I'm going to do more operations, but to introduce them all, I have to talk about truth tables. What is a truth table? Well, so if we have one variable, so here a truth table is a table in which the columns are labeled by propositions. So, for instance, P is a proposition, right? And then the rows are the values that this proposition can take. Well, you say that's only two values, 0 and 1, correct. And there is, it's not necessary, but it is the textbook sometimes diverges from that, but please try to follow this as a, most of you probably have never done this, so you can, it's fresh from start, so do it from the start correctly. No, not correctly, but do always systematically, put always truth higher than falseness. So we have 1 and 0. So we have two rows. Okay, P is either 1 or P is 0. But now let's see, how are we going to use this truth table? This is like nothing happens yet, right? But here is this not P. So that becomes the heading of my next column. So what is not P now? Once I know what P is, I know what not P is. Okay, so if let's go quickly. If P is 1, then we know that not P, that means P is true, then not P has to be false, so 0. If P is 0, meaning P false, then not P is true, so 1. So that's what a truth table does. So you start with your basic proposition, the propositional variables P, Q, and R, or whatever. There could be many more. And then you have applied these operations, and each time you apply operation, you can calculate the new value of this new proposition. Okay? So this was a simple one, but there are of course many more, and they are nothing. There's nothing going to be here that is weird. Perhaps one is going to sound a little bit weird, but it is something we know very well. So these are the standard ones. So the next one is P and Q, which is denoted with this kind of hat. But be careful, it's a head down, because we're going to also have head up. So this is P and Q. And the meaning is, of course, that if P is true and Q true, then P and Q are true. Okay, that is, so, but let's now think a little bit about to make a truth table out of this. So this is what this means, right? So here, now first of all, we have two variables, P and Q. Okay, you say, so okay, P can be 1 or 0 and Q can be 1 or 0. Now what is very important is, since they are variables, they have different names, they are independent. In other words, whether the P is true does not say anything about Q a priori. Okay, we remember this P and Q, we said from the beginning, they could be true statements, but they can also be false statements. And P and Q are normally two different statements. For instance, the statement, the sun is shining, that is P, and let's say Q is, it is Thursday. Okay, right? So let's look at, so if P is the sun shines, and say Q is, let's make something else, it is Sunday. So what does it mean, P and Q? That means the sun is shining and it is Sunday. So for instance, if it's Saturday, that would be false, right? Or if it's Sunday night, it would also be false. Okay? All right, so now as I said, the sun shining has nothing to do with it being Sunday. So P and Q are independent. How do we do this in a truth table? Well, P can be true, but then Q could be either true or false. So I have to give two rows, two possibilities. So remember, each row is a possibility that we can have for truth and or falseness. But these are the two possibilities that P is true. Now there are likewise two possibilities, namely that P is false and Q could be true, or P could be false and also Q is false. Okay? So where if you have one propositional variable, you have two rows. If you have two propositional variables, you have 4 rows. We will talk about what happens if you have 3 or 4 and so on. You could try to figure it out yourself, but let's keep going here. Because now we have at least all 4 possibilities, and now we can ask, what is this, P and Q? Let's think about this. Well, as I said, if the sun shines and it's Sunday, if both of these things are true, which is the case, I'm making this move, look here, and if you see in the left turn top table, it's 4 o'clock in the afternoon on Sunday, so it is true. Okay, so if P is true and Q is true, then P and Q are true. But now, what about other possibilities? Suppose it is still sunny, but it is already later at night, when it's dark, it's 10 p.m. or something like that. Then Q is false. What about P and Q? The sun shines. I confused my P and Q. P is false because it's 10 p.m., right? The sun is no longer shining, but it is still Sunday. Okay? So is P and Q true? No, because not both are true. So if one is true but the other is false, we get 0. Then this and this it has a name, conjunction. These are terms that we're going to use a lot. So I know I'm throwing a little bit of terms to you, but you need to know these kind of, okay? Conjunction. So the conjunction, the and, if one of them is false, then the conjunction is false. And this, therefore, the same, of course, is true in the third row. What about the fourth row, you think? Do you think if both are false, then somehow putting them together, they become true? No, of course not. So 0. Okay. Right? You're getting the gist of it? Well, what is the next one you can think of? I'm sure everybody realized the or part, right? P or Q, which we denote by this head, this little head upside down. Little V sound. So look, they're very similar. Be careful about that, right? P or Q, and this is called disjunction. The name is also very similar. But we do it so much you get used to this. Okay, let's think about that. Okay, what's the truth of that? So, okay, P or Q. Now we're talking about, still going on with this, the sun is shining or it is Sunday. Now, what if both are true? Sure, right? The sun is shining or it is Sunday. Well, you might say, should it not be one or the other? No, it's not an exclusive or. We call that exclusive or. Or involves also this case. Right? So for instance, if you go to a store and somebody tells you, okay, go buy an apple or a banana, and then you're in the store and you say, okay, I feel like an apple and a banana. Did you, when you said I'm going to buy an apple or a banana and you buy both, are you doing it wrong? Are you false then? No, of course not. So if one of them is true, if both of them are true, then P or Q is also true. But even more so, suppose now it is 10 p.m., okay, so we are a little bit later now, the sun is no longer shining, but it is still Sunday. So P or Q, the sun is shining, not true, or it is Sunday, true. So the whole thing is still true, right? Okay. And of course, it is the other way around too. Suppose it was now the next day, 24 hours later, the sun is still shining, hopefully. It's nothing drastic happened. But it's no longer Sunday. But still, the sun is shining or it is Sunday is still true. Okay. So what about if both are false? It is Saturday night. Well, the sun is shining or it is Sunday, neither is true, so now we have false. Makes sense, right? Okay. So these are now our three basic operations, although there's not the only ones. There are several other ones, like I said, exclusive or, which we're not going to treat that much, but it is discussed in the book, so please go look at it. But there's a very important one and a very confusing one, and that is this one. P arrow Q, and we read it P then Q, or better sometimes if P then Q, and we call this an implication. And that is somehow the most common usage that we have when we do logical reasoning. We use a lot of this if then, right? So for instance, let's make a different thing. Let P be Sunday. It is Sunday. It's Sunday. And let Q be we go outside. Normally I say we go to the beach, but nowadays you cannot really go to the beaches anymore, or less certain. Well, we don't know what we can do or not do in these days of uncertainty. But outside we can still go, even if you wear masks. Okay. If it's Sunday, so what is this now? Let's read the sentence. If it's Sunday, then we go outside. Because we can have free time, we go outside. Okay? So that's what this is supposed to mean. Okay, so we're going to make a truth table again. I'll start one over anew. And so how is it built? Remember, two possibilities for true for P and two falses, because we have 1, 0 and 1, 0. So do this systematically. And when I'll do with three variables, and then you see even better what I mean with systematic. So now what is P then Q? Okay, let's look at the possibility. Be aware. I should give you the answer already, but let's try to figure it out ourselves. Okay, it's not going to be always that obvious. Hopefully, when we discuss more this, when we say more rules and so on, a bit further in the course, you will be a little bit more accepting to this table here. So okay, it's Sunday. If it's Sunday, then we go outside. So it's Sunday, and okay. And suppose I decide to go for a walk. If it's Sunday, then we go outside. So if it's Sunday and I went outside, okay, what is this then? Is this a true statement? Yeah, if it's Sunday and you went outside, so yes, okay, so that's true. If P is true and Q is true, then this P then Q is true. let's look at the next one. Suppose it's Sunday, but I'm actually, in fact, in this case, I actually didn't go outside. I'm working now, and it's pretty hot outside, and I decided I'm not going to go outside. So what happens now? So P is true, but Q is false. Okay, we are in this situation now. What about the implication? If it's Sunday, then I go outside. Then I, let me make it I. That's false now, right? Because here's an example of a Sunday, today, that I didn't go outside. So this is false. If the P is true, okay, so these have, we call this the premise, and we call this the conclusion. If the premise is true but the conclusion is false, then the implication was false. And it was not a true implication. Now comes a little bit trickier thing. What happens if it's now, let's say, a day later? It's Monday. But I still went outside. If it's Sunday, then I go outside. So it's not true that it is Sunday, but I still are going outside. What do you think? Is this a true statement or not? Did I violate the statement by going outside on a Monday? No, the statement doesn't say anything about Mondays. The statement only says something about Sundays. If it's Sunday, then you have to go outside. Okay, it's only on Sunday. If it's Sunday, you can do something wrong. But if it's Monday, whether you go outside, doesn't matter. It's still true. Or whether you don't go outside, it's still true. If it's Sunday, then I go outside. But it actually is Monday today, and I didn't go outside. So have I violated my statement, if it's Sunday, then I go outside? No, there's nothing to do with it. So we get this is the truth table, always. So these truth tables, of course, are always the same, right? This is P then Q is always formed that way. Now, that is sometimes a little bit weird. People have a little hard time to understand. But have this example, you can still accept it. But I'm going to do one more example where you might no longer accept this anymore. Say P is a statement, the sun is square, and Q is a statement, the moon is, say, green. Clearly, both statements are false. Okay? So now, what about the statement P then Q? If the sun is a square, then the moon is green. What do you think? Oh, not the sun, not my sun, the sun. Okay? What do you think? True or false? Well, let's look at what the table tells us. Okay? Where are we? The sun is square. That is clearly false. The moon is green. Also false. We are in this line of the table, and according to this line, the implication is a truth. So if the sun is square, then the moon is green. You might say that is ridiculous, but that's true. It's a true statement. Because what this means is, if you start from a false assumption, then you can make whatever conclusion you want. That's something that politicians like to do a lot. Okay, so especially the ones that are unfortunately in charge nowadays. So this is the kind of thing that sounds counterintuitive, but it is still, if you look at formally, the sun is a square. Well, that is a stupid assumption. It just doesn't apply, and therefore you cannot get anything from there. So you can make a true statement, you can follow it by a false statement, the moon is green, but you could also, what if instead of green, we say the moon is yellow, which let's say she is, right? So this is now 1. So what is the value now? Well, now we are in this row, but it is still true statement. If the sun is square, then the moon is yellow. Yeah, the moon is yellow, that's true, but that had nothing to do with what the sun is like. Okay? All right, so I don't want to, you have to get used to this. So there is one more, and that is the biconditional. So with P, Q, we say P if and only if Q, and this is called the biconditional. So the implication is also sometimes called the conditional. If P then Q. If then is a conditional sentence, right? And P if and only if Q, that means What does it mean? Okay, it's best to see again what the truth table of it is. So this time I'm going to tell you what the truth table is, and then we can analyze it a little bit. But you can try to see whether you can guess it. Again, first of all, how do you make truth table? So remember, these are videos, you can stop them at any time and try to do it yourself and then see whether you were correct or not. 1, 1, 0, 0, 1, 0, 1, 0. I must make sure that I have all 4 possibilities. Okay, P even only if Q. What does it mean? P even only if Q. It says that if P is true, then Q be true, and that's the only way. So if P is true and Q is true, then P and Q is clearly true. If P is true but Q is false, false, right? Because if and only if means if one is true, the other must be true, and this is not the case. And here's the same thing because it's kind of symmetric, right? P even only if Q, whether you write it this way or you write it this way. We'll talk about this later, but it's supposed to be the same. Be careful, this is of course not true here for the opposite here, right? So Q then P is something else, completely else. We will talk about that. Okay, so let me get rid of this. But now comes the tricky part. What about the last one? If P even only if Q. Now if P is false and Q are also false, then they are actually then this biconditional is true. That's again something that you might find strange, but that is the case. And again, later when we do more operations, you'll see that it has to be this way. Okay. So what is for now? What you can think about it? Okay, there is an intuitive meaning of these not, and, or, if then, and even only if, but we have now formally defined them via these truth tables. So from now on, we always work with these truth tables. Now, how does it work then? Well, suppose, let's first now start with what happens if I have 3 variables. So now I have 3 variables. What are the possibilities? Well, if you think about it, P can be true, Q can be true, and R can be true. P and Q can be true, but now R could be false. What's the next possibility? P can be true, Q false, but R true. Q false and also R false. Okay? And then now we have all possibilities when P is true. Now can P be false? And then we can repeat the same thing for Q and R. Q and R both true. So now we're going to have 4 more of those, 4 falseness, where the same Q and R now. As the first, we copy the first 4 ones for Q and R. So either Q is true and R is true, Q is true but R is false, Q is false but R is true, and both are false. Okay? 8. 2 to the power 3. 4, 2 to the power 2. 2, 2 to the power 1. So it's the number of variables, P, 1 variable, 2 variables, 3 variables, that determines how many rows there are, namely 2 to that power. Okay? Because to have all combinations, we have to make sure. So how many if I have 4 variables? 16, right? Okay. So now let's say I want to make this statement. P or Q then R. Okay, what is the truth table of that? Now I cannot do that right away. That is true. So in order to solve this, we're going to break this down in smaller units. You see, I would write parentheses. In principle, I actually don't need to write parentheses. I'm not going to talk about it. It's kind of a little bit obvious, but in the book it says it very clearly, the order of operations. Okay, so please go look in that you understand what goes on. Okay, so how we break this down? Well, first of all, I need to know P or Q. Okay, that's the thing that I'm missing, because once I have P or Q, then I can do the implication with R. So when we have a composite propositional expression, so these are called propositional expressions. So it's a propositional expression. And what does that mean? Well, it is built up from propositional variables, in this case P, Q, and R, together with the operations that we had. Okay? So how does this work? Well, first of all, we have to make P or Q. Let's look at P or Q table. This is the P or Q. The P or Q table is this one. Okay, you can try to figure it out for yourself. But what I always say is, okay, if I have to make an OR table, and disjunction, then when is it false? It's going to be false when both are false, and all the other times it is true. So let's look at this. When is this going to be false? If both P and Q are false. Now, when does this happen? In these two instances. Okay, this is the two instances where both are false, and therefore everything everywhere else it is 1. Okay, so this speeds up a little bit, but you have to be careful, right? Because you have to be very systematic. Okay. Now, the conjunction, as I said, the implication, that is the one that is somehow hardest. And so please practice this a lot. I'm going to give you homework problems, and we're going to do a test on it very soon. How does that work? Again, let's see, when is an implication false? It's only one instance that it is false. I don't know what is microphone business. Okay. Namely, if P is true, but Q is false. That's the only case that I get falsitude. Okay, so let's see. So in other words, the order is important. Okay, so this means if the first one is true, but the second one is false. That is what I've looked for. Now, what is the order here? This is the first one. This is the second one. Let's double circle the second one. Okay, so this is the first one. And what I'm looking for, a situation where the first one is true and the second one, that is this guy, right? We have him already, there's no need to make him again, is false. So we're looking where this is a 1, we have a 1 in here and a 0 in there. Let's go line by line. This line, no. This line, oh yes, 1 and a 0. I know that this means 0, so I'll put it in red. That's a 0 here. This line, 1 and 1, no. 1 and a 0, 0. Okay, this one, 1 and 1, right? So we're looking in these two rows. Sorry, let me try to point here. So this row, we're looking now, this is the row that we're looking in, and this row, right? This is our first row. We're looking for a 1 in here, and then in the same row, column. This is the column that we're looking for 1s, and in this column we look for 0s in the same row. We have done this. We see that this happens in this row. It also happens in this row. It doesn't happen in this row because we have a 1 and a 1. In this row, again, we have a 1 and a 0. So we're going to have a 0 there. Okay, so 0. And what about the last two rows? No, because there is no 1 in that row, so I know it cannot happen. So that's it. These are the only cases that we have a 0, and therefore we can fill in the rest. These are going to be 1s. So I do it a bit in different color that you see. There are 2 steps that I did this. Okay, so I did this extremely formal. I can no longer do this by taking examples, P is this and Q is that and R is that, and then figure out what it is. Because in our daily speech, we cannot build such complex statements anymore. Okay, let me do one more. Hopefully it helps, but try it yourself now. Okay, I'm going to do a little bit more involved. I'm going to do the statement. Let me not put it now here. Give myself a bit more space. So this is the one I'm going to do. P, then not Q, or Q, then not R. Q, then R. Let me do Q and then R. Okay. So we have to break this down again in parts, and we'll look at it how to do. But let's start with building our. Make sure that we have the right table to start, the starting table. So in black, these are my starting table. I'm going to have how many rows? 8, right? So 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 1, 0. Please do this always this way so that you easily can compare what I do with what you do. For me also, I can much easier grade it than if you do this way. And also, that way you're not going to miss something. Because if you start randomly putting in 1s and 0s, you might forget one or write twice the same one. Okay? So now, we want to do this complex propositional expression to find out whether this, what the possible values of this are. But The problem is it's complicated, it's composite things, right? So we have basically two parts perhaps. We have this part and we have this part, and then finally we put them together in conjunction. So we have two implications. But the first implication is not between the variables themselves, it's by the negated variable. So I need to make a column for not Q first. Okay, so you see I'm unraveling the formula, going deeper and deeper inside the formula until I get to the basic variables, or sometimes to the negation. So now I have a negation, so I have to do negation. Now that's very simple, right? What's a negation is flipping the digits, right? It's flipping the bits here, that's negation. Okay, so that I can do very quickly. So now I'm looking again, this is the column that I have to work with, right? And so from this I built this column, okay? So I'm going to do this right away. 1 becomes a 0, 1 becomes a 0 becomes a 1, 1, 0, 0, 1, 1. Okay, one more time. Each time I flipped this digit into this digit, this digit, this. Okay, all right, that's not Q. Good. Next one. Now we have not Q, we can build P not Q. Now remember, it's an implication, and what I'm looking for is what are the two columns that are going to be involved? Let's mark them first, right? So there's a P and there's a not Q. This will be the P and this will be the not Q. So these are the two columns. And what I'm looking for, let me go back one more time to this P and Q. What I'm looking for is this part here. Let me make this row. I'm trying to find rows where we have a 1 for the first and a 0 for the second, because those are the ones that get 0 value. Okay, so let's go. Where are we? Okay, I'm going to point again. I'm looking for 1s in here, okay, and 0s in here. Oh, the first two are already of that type, so I'm going to have a 0 here and a 0 there. Anything else? Let's look at the next ones. This is a 1 and a 1, 1 and a 1, nothing. Zeros can never do anything. So those, I can never do anything, right? Because I need a 1 in the first column, so nothing can happen. Oh, that's it. Okay, good. So that means that the rest are 1s then. Okay? You do the whole, you go through the whole column, you find all the zeros, and if that's the only zeros, then the rest must be 1s. That is because a proposition is either true or false. That's why this is the case. Great. Now Q then R. Okay, Q then R. Sorry, can I change this? We haven't done anything yet, right? Okay, sorry if you have tried this already on your own. Yeah, okay. Then stop and try this one now. R then Q. I'm doing this on purpose because, okay, this is again, let's put it here. Now we're going to make this one. It's one of the components of my expression, right? R then Q. All right, so let's, don't want to get rid of these lines here, so let me put them back. Okay. It's again an implication. Now R is the first. This is R and Q is the second. Now be careful, Q comes here, right? These things gonna get a little bit messy because more and more stuff is coming, so sometimes the first, they're not always in the right order, if you understand what I mean. Okay, oh sorry, so this one was supposed to be double circled, right, the second one. Okay, so we're looking, let's say, repeat what we're looking. We're looking for this one, the first column, to be 1s, and at the same time 0s in this column. Okay, let's look. This one, no, this cannot be. Here is an occasion where we have that. So we have a 0 here. Remember, these are the 0 cases. We keep going. Here, no. Aha, here is another one. 0, and then the last one, if you look at it, no. Okay, I went through everything, so I found all the falsitudes or falseness, or whatever you call it. All the rest must be true. Good. So what do I have now? Oh, this was, sorry, some things fell. So we have this part, we can now put the whole expression together, right? The expression I'm interested in is P not Q, or R then Q. Now let's look at this table, the OR table. When is this false? Again, it is easier to say when it's false, namely when both are false. So now I'm looking for zeros in both. So what I'm talking about now, so I'm looking for, where are we? Oh, sorry, I'm looking wrong, that's why I can't find it. This guy, So we're looking in this column for a 0 as well as a 0 there. If there are zeros in both columns, then I get a 0. Let's see, does this happen? Nope. Wait, let me... which are the two ones? These two ones, right? Nope, 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 nope. Huh. Can it be? Yes, that can be. And so what we get 1, 1, 1, 1, 1, 1, 1. In general, of course, we're going to have ones and zeros there, right? In the previous case, you saw a couple of zeros, a couple of ones, and we'll see, we do this many times, so you'll see all kind of things can happen. But this is actually a special situation that we will discuss in the next lecture, and this is something that we call a tautology, meaning this is always going to be true. That's kind of strange, but these things can happen, okay? So, in other words, no matter what, and so here is, again, coming back to this false, why would you make false statements? This says that even if you make a false statement with P and Q is a true statement and R is a false statement, you make this complicated statement, I'm not going to try to do it in English, we could try, it becomes a true statement. Now, of course, it's almost a gibberish statement if you would do it, right? If you want to make, let's try it to see what we can do that, right? So let's stick to the, just to show you that it's actually, we cannot do it with natural language. So P was Sunday, it's Sunday, and Q was going outside, okay? Let me be with an R. Let R be the statement that, whatever. Why am I blanking on the statement? I'm thirsty. Because I actually am, that's why I think about it. Okay. So now, suppose it is Sunday, which is true, and it's sunny out, and I didn't go outside, that's not true, remember, I told you I didn't go outside, but I'm thirsty, okay? So what would this statement be? So, what the statement would be, okay, this is what, forget what I said about the actual things. Let's just make the statement. So this statement here, let's try to put that in English. We're using these terms. It says that. So, okay, I'm pointing. If it's Sunday, then I do not go outside. Or, if I'm thirsty, then I go outside. Can you figure out that this statement is always true? I don't think so, right? The only way to see that is making the truth table. So that is the whole point of these truth tables, and so, okay. So one more thing I have to talk about is we have this P then Q, right? We're gonna, this as I said, it's gonna be one of the most common type of expressions we look at, these implications, and therefore there are a couple of terms that we want to talk. First of all, what's the contrapositive? The contrapositive is going to be the statement not Q, then not P. So let's look at what this is in the case of Sunday and going outside again, regardless whether it is true or not, okay? So this statement says, if it's Sunday, then I go outside. What does this statement say? This statement says, if I do not go outside, then it's not Sunday, right? If I make it a habit to go outside every Sunday, if it's Sunday, I go outside. That's what I'm saying. That's what then, if I do not go outside, it cannot be Sunday, right? So this statement is actually implies this one. In fact, it's what we later will talk about next time, is that they are equivalent, right? That this saying this is saying this. I'm going to come back to this, but I want to already tell you that this is what we call the contrapositive. So in other words, the contrapositive is if you start from a true implication, and the contrapositive is also true implication. But you can do these are the good ones. These are the bad ones. So this is a good one in the meaning, in the sense you don't change the sense. This is the bad one. The converse. Q then P. That's what we call the converse. Now there we have to be careful. Remember the statement. If it's Sunday, then I go outside. This says, if I go outside and it's Sunday, is that the same content? No, because probably I go outside other days too. Believe me, I do. right? So the converse is not related to the actual implication, although very often people make this mistake, and when they see the implication and they say the converse, yeah. Okay, so for instance, an example is that. Okay, I don't want to do too many politics things, so let's do something like. Sorry, let's see what I can find one in there. So, for instance, here is let's do this one. Let's say I'm taking an example of the book, and it says the home team. Let's say baseball home team. If the home team wins, then it is raining. Okay, so if the home team wins, then it is raining. The converse would be that if it's raining, then the home team wins. And sometimes people have the idea that if the home team wins, then it's raining. That this means the same as that if it's raining, then home team wins. But that's not really the case, right? If you observe this play of this team, and you see that this home team, each time it wins, it was raining. Now, perhaps it only won twice, and just it happens to rain those 2 days, right? But if it's raining, that doesn't mean that the home team wins, because there were other times that it was raining and it didn't win. So the converse and the actual implication are not the same. That's why I call bad. They are not the same. And there's another one that is what we call the inverse. And again, this is often the reason that we mention this is because often people do think that they are the same. So let's go with the home team again. This original statement is if the home team wins, then it's raining. So perhaps so team wins, Q raining, okay? Okay, so let's see. If the home team wins, then it's raining. What's the inverse? If it's not raining, then the home team won't. If the home team doesn't win, then it's not raining. What do you think about that? Now, remember the situation where I said the home team won twice and it happened to rain on these 2 days, but there were 3 other days that they lost and it was also raining. So, if the home team doesn't win, then it's not raining. That's not true, right? Because there were times that they didn't win, but it was rain. Sorry, that's not what I was trying to say. If the home team doesn't win, then it's not raining. No, yeah, right. Okay. Okay, so this is now we will talk about these things later, and we're going to come back to them, but I just want to already give you an idea what they are. And so then let me see, I think, yeah, so as I said, the rest I will let you read, and I'm going to assign homework problems, and next time then we go dig deeper into this topic.